Good morning. So it's my first trip to NextRise. Every year I come, I'm impressed. We're discussing with my colleagues just now. Today we've discussed with many startups working on batteries, working on traceability for supply chain, for sustainable fuel production. All this on batteries, all these technologies, they are very, very important for sustainability, for the world to come. Huh? And this is precisely what I want to talk you about today. Huh? How we at Airbus, we imagine using these technologies to enable a sustainable aviation. Before I start, I want to give you a bit of a positive message. Huh? You know, in this era, we see a lot of issues, a lot of countries who are withdrawing from their commitment on sustainability. It's good to see that it's still happening. Right? And this is a report from the European Union, where they are actually stating that in Europe we are well on our target we are well on our path to reach our targets for 2030, which is 50% CO2 reduction compared to 20 years ago. Now, if you look more closely into this news, you see that we are talking about plans here, national plans. So just to reassure you, it's not only plans. There is also a report which has been measuring the emission in 2023. And they were also on a very good, it was also a very good news, the biggest drop in CO2 emission in the history of the EU. And this, with specific numbers, like 16% less emission from power and industrial installation, 25% almost in the energy sector, and so and so. Even increase in the capability of the EU area to absorb CO2. So it's very good, especially for an area so populated as Europe is. But not everything is rosy. If you look a bit deeper in the report, you will see that they are talking about aerospace also. And we are not doing good yet, right? So it's not so surprising, right? Because you know we had a bit of an issue during the COVID time. So of course, the aviation industry is picking up again. So when you grow again, of course, you're going to do more emission. And growing is the name of this industry, right? You know, it's been 50, 60 years that every 15 years we double the size of the industry. And it's continuing on this path. You have here a bit of figures from a report from Airbus, how we see the future of aviation. And if we zoom a bit more on Asia-Pacific, you see that in average, we see an increase in traffic of 4.5%, which is exactly what you need to double the industry every 15 years. So if we fast forward to 2050, the size of the industry in Asia-Pacific will be fourfold compared to today. And of course, the emissions, they are following this trend. Right? And so we need to do something about it. Not to worry, we have a plan. And this is what I'm going to explain to you today. I have 2 points. First, what is the plan? And then the role of technology that can play in this plan for aviation to reach net zero. And so this is, amongst ourselves, a very well plan. Right? It's not an Airbus-specific plan. This is overall industry, aviation industry. We have a long-term aspirational goal, which is to go to net zero emission by 2050. And to reach this, we have identified five main pillars, main levers that we can activate. One of them is very famous at the moment, right? This is a green one. It's half of the solution. We'll rely on the scenario of adoption of sustainable aviation fuel in the aviation industry. But the three others are more technological in nature, right? You have replacing the fleet, because of course, the more recent, the more new the planes are, the more efficient they are, and the less you consume. It's a bit like the cars that we saw just now. There is usage of more advanced type of technologies, and this is why we are here today, and what I was saying as an introduction, all these new technologies, exciting technologies on electrification are going to be useful, and I will explain this a bit more later. And then there is also better usage of the airplane itself, right? If you're not stuck in traffic jam, you consume less fuel also. So I'm just going to give you a bit of example, but before I give in this, I dive in this, I also want to highlight I was a bit negative to start with. Okay, Europe is on a path for sustainability, except for aviation, but it's very it's due to the COVID issues. Right? If you look at where we are coming from and where we are today as an aviation industry, we've already reduced our CO2 emission by 50% already since 1990. And this is not surprising because every 20 years or so, you have a new generation of aircraft. And these aircraft, they are 25% more efficient than the previous generation. And so this is precisely the main levers that we need to activate. I cannot resist, of course, to put this picture of a Korean Air A350, which they just ordered. Right? These airplanes, newest generation, 25% more efficient than the plane one generation sooner in the 2000s, 25% more efficient than the planes that were in the 1980s. And the next plane that we are going to do, objective is to be 25% more efficient also. Second lever, I was mentioning, the biggest of them all is 50% of the solution will be in using sustainable aviation fuel. These fuels, they can come from three main origins. Some of them, they will come from recycling some waste, used cooking oil, and transforming them back to sustainable fuel. Most of the solution will come from biogenic sources that you need to transform through various thermochemical processes to sustainable fuel. And then to finalize it, at the end, we'll add some sort of power to liquid type of fuel. The challenge is immense. We need, overall, as the industry, something like 300 to 400 million tons of fuel to be produced in 2050 if we want this scenario to be realized. Today, we are around 1 million tons, right? So the path to cover is massive, but it's happening. Huh? We see this, and Airbus, ourselves, we are very active in trying to make this happen. The third pillar is if you have an airplane, if it's efficient, you still need to make it to make the best use of it. Right? And I'm illustrating this with, you know, when you fly, it's not a straight line. Most of the time, you will have different level of altitudes, different zone, depending on what the air traffic is going to tell you. And you will have like your optimal flights that everybody thinks that we are flying. Since we are in the air, I go up, I fly straight, I go down, I land. This is the most efficient flight that you can ever have. And most of the time, you will be on this flight path where you have several levels, several zones where you are handover between different countries controlling your area. And then once you reach your airport, of course, traffic jams, so you have a holding pattern before you can land. And it's estimated that this type of operations is wasting up to 10% of the total jet fuel that we are using on the planet. And so estimation is a wrong word because it's been measured during the COVID times, because this is one of the only benefits of this is it allows us to measure what it is to fly with no traffic jam, because there was very few planes at the time, and the efficiency in operation that we measured at this time was 6%, so it's massive. And this is precisely what we do in Europe also. I want to highlight how important it is, because if we use the airplane more efficiently today, it's CO2 that we are saving today, and it's the carbon budget of humanity. And you know, this is what the Paris Agreement is all about, and to limit the overall carbon budget from humanity. And so the small adjustment you see here, we've done some flight tests between Paris and Stockholm in Europe. So we are flying over the most crowded part of the European sky. And we've done that for hundreds of flights. And the modifications that you do, they are very, very minor, right? You can barely see them on this diagram. But we are getting like faster climb, higher type of descent also. So the higher you fly, usually the more efficient you are. The flights are slightly higher also, and they are a bit straighter. You remove, like here you see, they don't have this kind of passing point here. They go on the purple line here. And just doing this, we save 5% of the fuel consumption on this particular flight. Right? And so this is massive, and it's something that we need to implement all over the world to minimize the impact of aviation on the ecosystem. Then, I've been very quiet on this one, but once you have the best airplane, you have the best technology on board of your airplane, you operate it as best as you can, you put some sustainable fuel in there to limit your impact on aviation, there will still be somewhere like 5% emission that we still need, residual emission that needs to be offsetted. And the best way to do this is to try to do carbon capture, direct air carbon capture. And so I'm illustrating this with a project company in the US with whom we have been partnering, 1.5, what they are doing. There are some plans to absorb million tons of CO2 through this massive Dyson type of things. Right? And there is no scenario where we can escape this type of activities. So this was a plan for aviation. Right? We can reach net zero by 2050. We have several levers. And today I want to highlight a bit more the one on technology. Right? So this is the one I highlight here. And the impact it can have, it's 25% of the solution. And you see it starts in 10 years from now, give or take. Right? This is the next generation type of aircraft that needs to come to our airlines. And what are we talking about? Right? So first remark, it doesn't exist. It's an aircraft for 10 years from now. So we are still on the drawing board. We are selecting technologies. And what we imagine is it is going to look something like that with futuristic type of new engine, open rotor type of engine. It will be new material. It will be maybe more efficient, better aerodynamics. And let me explain a bit what are the levers that we need to activate if we want to have a better aircraft. And the best is to start from a very simple engineering equation, right? The range equation, the Breguet range equation that we use to design airplane. And there is 3 parameters basically to compute what is going to be the range of your aircraft. And they relate to aerodynamics, to propulsion, and to weight. And it's no surprise. Huh? The lighter the aircraft, the more likely, the less energy you need to power it. Right? The more efficient your propulsion, the better your propulsion, the longer you can go. And also, the better your aerodynamics, the less you need energy to actually propulse it. And this is exactly what we are looking at. Right? If we go back to this picture, let me start from the upper left. Efficient fuselage, more newer type of material. We are working on the weight here. And there is still some margin to win maybe 5% efficiency by reducing the weight of the aircraft. We've been working on this relentlessly over the past 50 years, and we continue. And we saw some startups also during this week that are interesting in this domain here in NextRise. Huh? The second part is we work on the wing, more efficient type of wings. It's massive, the type of savings you can do, and basically you want them to be thinner and longer, and this is potential 10% savings also in there. Third one is propulsion, like I mentioned, and in this one we partner with some propulsion company, GE and Safran or Rolls-Royce, and they come up with some new concept. The bigger the engine, the better, which can save up to 25%. Now, if you add up everything, you're going to tell me this is more than 20%, right? And this is because you cannot just stack the benefits. Right? At some point, you need to integrate and do some trade-off between the different type of technologies. Right? So once you put an engine on the wing, the bigger the engine, the more impact it has on the wing, the less you are free to do the most optimal wings that you can do. Right? So there is a bit of trade-off, and our hope is that once we do all the trade-off and the integration, we reach 20 to 25% savings overall. Now, I mentioned 2 more points here. Once you have the best airplane on the planet, right, you still need to equip it with systems that are going to allow him to operate in the type of airspace I was describing, to have the most efficient type of operations. And for this, you need a certain degree of automation, you need a certain degree of connectivity for the airplane to communicate. Right? So we work a lot on systems, and also systems, they have an impact on weight. Right? You know that the cars today, they are more and more heavy because they are embarking more and more systems on board. It's the same story for an aircraft. Right? So we work a lot on this to mitigate the impact on the weight of the plane. Right? And the last point is related to the first lever I mentioned. Right? If we want a sustainable aviation, we want people to use the newest airplane possible. And if we want them to use this airplane, you need to be in a position to produce them as fast as possible. Right? So we need to improve our industrial systems to be able to produce more airplanes faster to renew the older fleets. So now I just want to give you a bit of pictures and highlight on the kind of technologies we are working on, right, to inspire you a bit before lunch. If we go to propulsion, so I mentioned we are working with our partners to test some new engines, and the most promising ones, the ones that we are hoping are going to be mature enough for us to embark on the next generation aircraft, as the one you see on this picture here. So this is open rotor, and the idea is simple, right? The larger the engine, the more efficient it is. Right? But the larger the engine, at some point, the nacelle that is covering the engine starts to be too heavy, and you have a trade-off between weight and efficiency of the engine. And at some point, you're reaching the limit of what physics can do. Right? And basically, once we do the 350 and the engine we have on the 350, we have reached this limit already. So the next step, you have to go for open rotor type of engine. So basically, infinite size of engine, if you want. Right? And so this is what we are trying to up. And this kind of new concept, of course, it comes with some associated difficulties. Right? If the engine is not contained anymore, you have a bit of a certification issue. So we at Airbus, we are very much involved with the engine producer to try to do some certification type of tests. So you do some testing in a wind tunnel. We've been running this for several months already, and it's very promising. And then the next stage is what you will see on this picture. We are going to use our S380 first airplane ever manufactured as a test bed, and we are going to mount one of these engines, and we're going to test fly it for a few months. The second thing is once you do where Airbus is involved in this, you have new type of engine. The propulsion, it needs also to be efficient. There is two ways of being more efficient. Right? The engine itself is more efficient, and also what you ask of him is more efficient. Right? And you know, an airplane, beyond propulsion, you have a lot of energy need also, right? For activating systems, for the in-flight entertainment, for the air condition on board. And so the more you can relieve the need of this energy on the engine and put it back on some other type of energy sources, the better it is for the engine. Right? And so for this, we are working towards hybridization, energy management system, right? And there will be a bit of battery system and electric power on board of the next airplane. Right? The last one we work on is the integration, the aerostructure integration itself. Right? These kind of engines, they are massive. They start to be so massive that at some point they are as big as a fuselage, and it has an impact on the overall design of the aircraft and the size and the shape of the wings. Right? You can have some wings that start to be very similar to hull wings type of things. And so this is the next thing. We work on aerodynamics a lot. Right? I talked about the wing. I give you here a bit of an example of a demonstrator we did almost 10 years ago on the A340, right? And you see here on the funny things that we added at the end of the wing. Right? And basically is to test, can we work on this laminar flow, you know, the efficient flow around the wing to increase the aerodynamics. And we've done that 10 years ago, testing different type of things, as passive type of laminar flow mechanism as well as active. And the most important is to actually test it on an airplane, because you know, if you just do it on the lab, you cannot get the actual results. So we were monitoring exactly what are the type of how you say that, the manufacturing defects that you can accept, so that the behavior of the wing is still acceptable. Right? And so this kind of information we're taking back, and now we have a program that we call Wing of the Future, which is working on the best of efficient wing possible, so as long as thin as possible, as light as possible also. I mentioned weight, so you need to work on the material, you need to work on the structure, and as manufacturable as possible also. I go back to my point where you need to manufacture this thing if you want the new airlines to take the new plane. Last item I want to mention in more details is weight reduction. I mentioned the fuselage. Fuselage is a massive element in terms of weight for the airplane, and we've been working on new type of material. So it's not completely new, but it's materials that we don't use widely in the plane today. It's thermoplastic type of composite. Main advantage, it's lighter, it's easier to put in place, it's recyclable also. We had some people on the stage earlier that were talking about the circularity, and it's an important aspect for us also. And also, since it's easier to manufacture, you can start to pack more functionality in the same type of modules, and so it's helping also to increase the manufacturability of the aircraft. And what you see here is a demonstrator that we did earlier this year. You see the size and the scale of the kind of things you need to do to demonstrate that the technologies that you develop, you can also implement them at industrial scale, and then you can go to the next stage and you can prepare them to be ready to be onboarded for an aircraft program that will start in 5 years from now. I mentioned briefly about systems. I gave you a bit of an idea of how an airplane is supposed to integrate in the airspace so that we can save these 5 to 10% emissions due to traffic jam. There is even more that we can do, right? Imagine you have sufficient connectivity capability between two aircraft so they can discuss together, so they can fly together. Then you can start to mimic what the nature is doing. And this is what we've been doing with two A350s, what you see on this picture. We have been flying over the Atlantic with one plane behind the other to try to recover a bit of this wake energy. And this, again, just this is saving 5% fuel consumption for crossing the Atlantic. So it's a massive potential new way of operating aircraft, enabled by new type of connectivity and systems that we are onboarding on our aircraft. And it's going to help usher aviation into this a new era of sustainable aviation. I want to finish with a bit of an opening. I've been discussing a lot on new technologies for next generation aircraft that we imagine appearing in the next 5 to 10 years. Then we need to look even further, right? And you know, in Airbus, we've been pushing for quite some time already. We are a big believer in the hydrogen ecosystem. I know Korea is also a very big country for the hydrogen ecosystem, right? And we are still pushing this very, very much. We have a lot of work ongoing on this hydrogen aircraft platform that we've been developing. We have unlocked most of the technological blockers, so we know how to do, you know, the cryogenic tanks. We know how to leverage cryogenic technologies to use this to make the power transmission more efficient. We have worked a lot with fuel cell companies to make them more efficient so that they can produce the type of power we are needing. You know, just on this picture, the target that we have is 2 to 3 megawatt power for each of these engines. But this type of solution, it's technically possible today. We are convinced this is the end goal, right? Because, you know, remember I was saying sustainable aviation fuel, we need 300 million tons of it. Half of it is going to come from power to liquid, if you want, which is from hydrogen. It makes no sense to use hydrogen, combine it to fuel, to burn it later, if you can burn it directly in an engine, right? And so, in the end, aviation will be powered by hydrogen, but you cannot go faster than the music, as we say in French. Right? And if you don't have hydrogen available at airport, if you don't have green hydrogen available at a reasonable price, the economics of an aircraft running on hydrogen is not going to be efficient for the next decades. Right? So it's going to come a bit further, but it's still the end game for aviation will be an hydrogen-powered aircraft. And I will conclude just back to this slide. Right? We have several levers. Sustainable aviation is a big one. Replacing the fleet with a newer one is very important. But technology has a key role to play, right? And I hope I convince you on this. Right? It will play a key role. We have all the elements aligned already. And we will have a newer airplane in 10 years from now and an hydrogen airplane in a bit later from now.
Thank you for your insightful presentation.